Okay, I'm going to go through the FRQ answers for the practice test, and Mr. Koo did an excellent job of writing this all out, so I'm just going to kind of review what it is and point out a few things, but his answers are perfect on here. So first question, methylamine is a weak base, okay, and it's that little amine part right there that's making that a base for us. Okay, there's going to be a lone pair on that nitrogen, and that's where it can accept a proton. And it has a Kb of 4.17 times 10 to the minus 4 at 25. Okay, so write the chemical equation for what happens when you put it in water. So here we go. So you have ammonium plus water. It accepts a proton. It goes this way and becomes the methylammonium and hydroxide. So that should be a kind of standard thing. Second thing is identify a Bronsted-Lowry conjugate acid-base pair in this reaction. So you have to stop and say, okay, well, one of these two, you either have to identify those two, okay, or identify these two, okay, and if we go those first two here, like you say, then the methylammonium, methylammonia, that's the base, and the methylammonium is the acid. Or if we go for the other two, then we say H2O is the acid, as it donates the conjugate base is OH minus. So either one or the other, you have to identify those. Now, part 3, a sample of methylamine has a pH of 12.26. What's the molar concentration of methylamine in this sample? So the fact we're given a pH, if you're given a pH, then pretty much you can turn that into a pOH. You just did that here, subtract from 14. And if we know the pOH, we can find the OH minus concentration, and that's, 10 to the negative 1.74. Okay, but we know because of our sample here that if I've made that much hydroxide, I've also made that much methylammonium. So we know both of those. And what we're going to do is go back and do an icebox, and I wanted to show that piece. So I just recopied the equation here. Now the icebox, because we know the OH is 1.8 times 10 to the minus 2, and we know that, every time we make an OH, we're also going to make a methylammonium. So both of these are 1.8 times 10 to the minus 2, and we started with 0 of each of these. Then our change must be plus 1.8 times 10 to the minus 2, plus 1.8 times 10 to the minus 2, minus 1.8 times 10 to the minus 2. So where's X? X is actually this guy way up here, the methylamine. And that's what we're trying to find, is find the concentration of the methylamine. So X is that, and so our answer we're going to be X minus 1.8 times 10 to the minus 2. So we're trying to find what's the molar concentration, so that's that X. So now you go back here, and you can see that he's put all that into the Kb expression that comes from this equation, and just chug, and you kind of end up with the methylamine concentration being 0.79. So it's a little different, little twist on an icebox, but nothing too surprising. Okay, for part B, if you have a 0.1 molar and 0.001 moles of KOH, now KOH, we don't care about the K, we just care about the OH, and that's added to 1 liter of 0.2 molar methylamine. What's the pH of this solution? So you can see what's happening. We have a weak base and a strong base added together, which means we have two initial values when we get to our icebox. So here's our icebox. And like we've done before, we just have our initial concentration 0.2, but we also have an initial concentration of hydroxide, a small number. And that's the only difference. Now it's minus X plus X plus X. We get our values. We substitute it into the Kb expression, and then we solve for X. And the OH minus concentration is 0.1 plus X, which is 0.0834. So there's where we get our concentration of hydroxide, and therefore we get our pOH and subtract from 14 to get our pH. And that's that kind of problem. Okay, then we go back to part C. If we have 50 grams of methylammonium chloride is dissolved in water. Now, methylammonium chloride, you say, okay, I don't care about the chloride. The chloride is not part of the problem, okay, because that's going to come from the strong acid. HCl, so it's the other part here. So it's really, we're saying methylammonium ion. So that's what's important. So write the net equation for this. So there's a net equation. So the methylammonium, which is the conjugate acid of the weak base, is going to donate to the water, okay, and we're going to get methylamine plus H3O plus. So that's the standard kind of conjugate. Now this is the conjugate acid of a weak base. A lot of times we do conjugate bases of weak acid, but they both work. Okay, now we've got to find the value of the Ka. So Ka is Kw over Kb. Okay, and we know the Kb from the first part of the problem. Okay, that's the 4.17 times 10 to the minus 4. So here we have a value for our Ka. So far pretty easy points. Now calculate the pH of the solution. So now we get to an icebox problem, okay, except we have one little thing, and that is in our icebox, we have to get that concentration of the initial stuff, you know, the ammonium, the 4.93, and that has to come from doing some old stoichiometry. So you got to say, you got to take this guy, you have to calculate, you know, add together the chlorine and the nitrogen and the carbon and the 6 hydrogens, and we get 67.52. We have 50 grams. We're going to use the molar mass to turn that to moles, divide by 0.15 liters, okay, which we get from the 150 milliliters. So all that is done just so we can get that initial value here of the 4.93 molar. After that, it becomes an icebox, standard icebox, 0, 0, minus x plus x plus x. So 4.93 minus x, x, and x. Okay, this is a really tiny k, so we can ignore x, and we solve for x. And x is our H plus concentration, so the pH is the negative log of that number, so the final thing is 4.96 as our pH for that solution. Okay, and that's all question 16. Okay, question 17. Now that deals with these acids, and we should stop and look at the acids quickly. Each one of them has a COOH. Okay, these are all carboxylic acids. Okay, so that part's the same, but what's different is the chlorines. So here's a chlorine hanging on that carbon, and here's 2 chlorines hanging on that carbon. Here's 3 chlorines hanging on that carbon, and the first one has none. So the first, which is the strongest acid of these 4? Okay, and just quantitatively, so that means we're looking at these pKa's. Okay, and the pKa's, you know, the smaller they are, the stronger that acid. In fact, for a strong acid, it's actually going to get way negative. Okay, negative pKa. So small ones. So this is going to be the strongest of these, you know, just because it has the lowest pKa, or in this case, the most negative pKa, even though we didn't get to actual negative numbers there. So the smallest pKa would give us the strongest acid. The second one is, what's the reason for that? Well, these extra chlorines on here, we can see what's going to happen is those are going to pull electrons away from the carbon, and it's going to polarize that OH bond. Okay, and if it polarizes, that means this hydrogen is not going to see that pair of electrons very much, and so it is going to be more likely to leave, and so this acid will be the best donor, and that means it's going to be the strongest acid. So the weaker this bond, the OH bond, the stronger the acid is considered. So the increased Cl's polarize the electrons away from and weakens the OH bond. So H plus is more easily removed, meaning it's a stronger donor, stronger acid. And that's 17b. Okay, for the next part here, for C, consider these salts, sodium CH3COO and sodium CCl3COO. Okay, so first thing, we don't care about the sodiums again. We care about those ions. Okay, so we're talking about conjugate bases of some acids. And here's CH3COO, so this is this guy. Okay, after this H is taken off. And this with 3 Cl's, this is this guy after that H is taken off. Okay, so we're talking about those two. If we had 0.1 mole of each to make a 1 liter solution, which would have the lower pH? Okay, lower pH means the most acidic or the least basic of each of these. Okay, so lower pH. So this guy is the stronger acid, so it should be a weaker conjugate base. This is a weaker acid, so it will have the stronger conjugate base. Okay, so it's this guy here is going to be the weakest of the weaker of those two bases, so that's going to have the lower pH. And why? Okay, because this is a stronger acid, and so it's going to have the weaker conjugate base. And that is the answer. And that's everything.